Okay. Hello, everyone. I'm Zhang from Nanjing University. I'm happy to be here to present our work on a no black box approach in finding cross-rule optimization bugs in Datalog engines. This is the joint work with Linzhang Wang from Nanjing University and Manuel from National University of Singapore. Datalog is a popular logic programming language supported by the deductive database system. Datalog has been applied in many important domains, such as program analysis, distributed systems, program understanding, big data, and some other important domains. So it is crucial that the Datalog engines work correctly. I use an example to introduce what is Datalog. Suppose you want to find the reachable node in a graph based on its edges. Then you can use this Datalog program. In this program, the relation edge presents a real edge between the two nodes in the graph. For example, if there is a fact edge 1, 2, means there is an edge in the graph between node 1 to node 2. This program takes 4 edges as input. There are 2 rules that define the relation reachable. The first rule computes the directly reachable node based on its edges. And the second rule computes the indirectly reachable nodes based on the existing reachable nodes and the edges. For example, node 2 is directly reachable from node 1 due to the edge 1, 2. And since there is an edge from node 2 to node 3 becomes indirectly reachable from node 1 through node 2. Executing this program with the Datalog engine, we can derive all the reachable nodes in the graph. There are many major Datalog engines, and these 4 are among the more well-known. Soufflé is widely used in many projects, including Deopt, a Java static analysis framework. CozoDB is designed to support machine learning and has obtained over 3,000 stars on GitHub. DDlog is developed by VMware with over 1,000 stars. Muse was used as part of this a well-known constraint solving tool. Many cross-rule evaluation strategies are applied in Datalog engine to efficiently evaluate rules. For example, the bottom-up method evaluates all rules to derive the complete set of results. In contrast, the top-down method only evaluates the rules that are related to the output relation. There are also many optimizations, such as magic set transformation, which improves performance by rewriting the rules. These optimizations typically require careful consideration of the relationships between rules to ensure the correct execution. Our goal is to find cross-rule optimization bugs in Datalog engines. Logic bugs can cause Datalog to silently produce incorrect results for a given program. And cross-rule optimization bugs are logic bugs that are caused by cross-rule optimizations. The main developer of Soufflé also emphasized in the recent keynote that designing novel automated testing tools for Datalog engines is one of the main open challenges in this domain. Test case generation and test oracle are 2 main key challenges in fuzzing, both of which we aim to address. So let me first introduce what is logic bug. This test case triggered a logic bug in CozoDB. After the first 3 rules, there are 3 facts: node 1, edge 1, 1, and edge 0, 1. The expected output for this test case should include both 0 and 1. However, CozoDB only generates 1 as the result. The developer of CozoDB gave us feedback that the worst thing a database can do is to give wrong output. This bug was caused by an error in the sim-naive algorithm, which is a bottom-up evaluation strategy. An intuitive idea to detect optimization bugs would be to apply differential testing. Differential testing means providing some inputs to 2 or more comparable systems with the expectation that they produce identical results. But different Datalog engines share only core features, so it is impossible to test other important features. Most Datalog engines do not offer optimization options, making it challenging to apply differential testing within a single Datalog engines. To detect cross-rule optimization bugs in Datalog engines, we propose a new black box test approach named Incremental Rule Evaluation. We incrementally build the test case and individually evaluate the new added rule. This approach allows us to disable all optimizations that would typically be applied when multiple rules are present, while also enabling the generation of complex test cases that produce non-empty results. The core idea behind our test oracle is to execute each rule in the test case individually, thereby disabling all cross-rule optimizations. This is the overview of our approach. Our approach begins by generating the initial inputs and the definition of corresponding relations. Then we enter the iterations and generate a rule in each round. To determine the execution order of the reference program, we construct a precedence graph in which each node represents a rule and each edge indicates a dependency relationship between the nodes. The reference program is then evaluated based on the order determined by the precedence graph to obtain the reference result. Finally, we evaluate the optimized program and compare its output to the reference result. Any discrepancy indicates a logic bug. Now I provide more detailed information on our approach. To begin, we initialize the input and generate the corresponding relations. Here we generate two facts as input, in0 and in1. In the first iteration, we generate the first rule based on the initial relations. Here we define a new relation as the output of this rule. Here is A. This will introduce a new relation into the test case. We derive the result of this rule from the Datalog engine and check it. If the result is empty, we remove the rule with a high probability and generate a new one to avoid having rules with empty results. This is necessary because an empty relation can lead the Datalog engine to compute an empty result for other rules that's dependent on this relation. However, some bugs require an empty relation to be triggered. So we introduce this probability. We also verify that the newly added rule is valid and does not cause any semantic error, which can be challenging in random test case generation. The random method lacks knowledge of the facts derived by rules, and a certain specific value can trigger errors, such as division by 0. Then we add this rule to the optimized program and obtain the optimized results. We verify that the results obtained from the reference program and the optimized program are identical. In the second iteration, we generate the second rule and do the same things as that in the iteration 1. We can see here the reference program only contains a single rule, while the optimized program contains 2 rules. The reference program also requires additional facts as input. Here is A0 and A1, which are the outputs of the first rules, as relation A appears in the rule body. Last, if there is an iteration N in which a discrepancy is found between the results of the reference program and the optimized program, we consider that the test case to have triggered a logic bug. Or if the number of iterations reach a predefined limit, indicating that the optimized program is sufficiently complex, we end the generation of the current test case and move on to the next one. With this approach, we generated this motivating example step by step and detect this bug in the fourth iteration. However, there are cases where our approach cannot be directly applied. Specifically, if a previous rule depends on a newly added rule, we must re-evaluate these rules to ensure that all rules reach to a correct fixed point. The execution order of these rules determine whether the correct fixed point can be reached. This is an example that involves regression, with the negation palace outside this regression. This is a precedence graph that illustrates the dependency relationships between the rules. To determine the correct evaluation order for each rule, we use a well-studied solution from Datalog engines, stratified Datalog, which is designed to handle negation in Datalog engines. Stratified Datalog first divides the precedence graph into different strata, where rules in a lower stratum depend on rules in a higher stratum. Rules that form regression are placed within the same stratum. Then we eschew the rules sequentially from the top stratum to the bottom. For rules within a same stratum, there is no specific execution order if there are no dependency relationships between them. For rules involved in regression, we need to evaluate them iteratively until no new facts are derived, indicating that all the rules have reached a fixed point. The input for each rule should consist of the necessary facts derived from the higher strata as well as the same stratum. Finally, for this program, we will obtain the following execution order. So for the newly added rule O3, we need to re-evaluate R0 first, then iteratively evaluate R1 and R2 until there is not any new fact is derived. Means this regression reaches the fixed point. However, if there is negation within a regression, we cannot compute the fixed point by evaluating the rules individually. For example, we add a negation at the rule R2. This case falls outside the scope of stratified Datalog, and most Datalog engines do not support this language feature. This is supported by another language, Prolog. So to address this challenge, we put all the rules in this regression into a single reference program to derive all the facts generated by these rules. While this approach may not directly detect bugs within the regression itself, it can still identify bugs arise between the regression and other rules. We implemented our approach in a tool named Deopt and selected 4 major Datalog engines for evaluation. And then evaluated it with the following 3 questions. First, how effective is Deopt in finding new bugs? And how does Deopt compare to the state-of-the-art approach? And last, how do Deopt's components contribute to its overall effectiveness and efficiency? For the first question, Deopt found 30 unique bugs in 3 major engines, and 13 of them are logic bugs. We also found a logic bug in DDlog. However, this was the only one bug that a state-of-the-art approach found in DDlog, and it has not been fixed yet. Here is the state of the bugs found by Deopt. 6 bugs have been fixed, and 13 have been confirmed. We conduct a comparison for the second question. queryFuzz is the state-of-the-art approach to detect logic bugs in Datalog engines. We found that out of the 13 bugs detected by queryFuzz, only 1 could not be identified by our test oracle. This bug occurred within a single rule, making it unclear how to apply our test oracle in this test case. And for 13 bugs found by Deopt, 5 could not be found by queryFuzz. There are 2 reasons why queryFuzz missed these bugs. First, its mutation approach is limited to conjunctive queries, which means some language features are not supported. Second, queryFuzz is unable to prevent the application of certain optimizations, so making it ineffective to detect bugs related to those optimizations. Our tool offers multiple configurations to control the testing process. Here we present only the most important one. We compare the efficiency of our incremental test case generation approach with the naive random one. For the random approach, we generate the entire test case at once and then execute each rule individually to create the test oracle. We run this experiment for 24 hours with different test case size. We have 3 metrics. The first is the total number of test cases generated by these 2 approaches. And the second is the total number of valid test cases. The last is the total number of test cases with non-empty results. We found that while the random method always generates more test cases, our incremental approach always produces more valid test cases on Soufflé and more test cases with non-empty results on DDlog. Lastly, let me conclude my talk. This work aims to identify cross-rule optimization bugs in Datalog engines. We proposed an incremental rule evaluation method that generates the test case and the test oracle in the same time. Our approach found 30 unique bugs across 3 major engines and demonstrated the ability to generate more valid and non-empty test cases compared to the random method. That's all. Thank you all for listening.
All right, we have time for a few questions. And again, please come up to the mic if you want to ask a question.
Hi. I mean, also in relation to the talk I gave before, how much effort did you have to spend in order to target these different Datalog backends? Like, how did you address that in the test generation?
OK, I think our approach is easy to implement, as we just reuse the Datalog engine under test, and we just split the rules and run them one by one. So we don't need too much effort to implement the tool.
But, so I'm not sure I understood. So you generate the rules, right?
Yes.
And you have separate generators for each Datalog backend, or do you generate them in one dialect and then translate between those, or how does that work?
You mean for different Datalog engines?
Yes.
Yes. I think the core algorithm can be reused by different Datalog engines, but the generation of the generation of the test case of each Datalog engine still needs some effort.
Okay, thank you.
OK, well, let's thank our speaker again.